Welcome to the Deep Dive. Today, we are plunging headfirst into, well, one of the most persistent and costly headaches facing anyone trying to scale modern industrial automation.
Mm.
I'm talking about the silo problem.
Mm.
If you've ever managed a facility, maybe with robots from 3 different vendors,
Mm.
you know the pain, that fragmentation.
Exactly. And our mission today is really to unpack that fundamental challenge, this platform fragmentation where, every specialized robot basically relies on its own custom software stack, its own ecosystem,
Right.
and then introduce a unifying concept, looking at General Robotics, formerly Scaled Foundations, and their platform, GRID.
So our goal for you, the listener, is pretty simple.
Yeah.
We want you to walk away understanding not just what this silo problem is, but why a modular approach using AI skills, large language models, and deep orchestration promises to turn these complex, high-cost robotic fleets into something, well, far more manageable.
Yeah, behaving less like these unique, expensive appliances.
Exactly, more like, say, interchangeable software modules.
Mm.
Okay, let's unpack this operational nightmare then. Why, despite, billions poured into automation, are large-scale robot adoptions, especially when you're mixing different hardware types, still so agonizingly slow and, frankly, hampered by cost?
Yeah, it's really all about vendor lock-in and the sheer cost of heterogeneity. The sources we looked at are very clear on this. We've seen just tremendous hardware innovation, right?
Sure.
But that explosion has led to a massive proliferation of isolated software stacks. So if you buy a mobile warehouse bot from vendor A and, say, an assembly arm from vendor B,
They're speaking different languages.
totally different languages, different data formats. They require separate DevOps teams just to manage them. It's complex.
So, okay, we know the symptom is fragmentation. But give us a punchy example, like what's the real financial hit here? What does this actually mean in terms of integration cost and, I guess, risk?
Well, the real cost, it really hits you during updates and the integration itself. I mean, imagine you finally managed to integrate those two vendors, right?
Yeah.
Maybe it costs 6 months of precious engineering time. Yeah.
Yeah, a huge investment.
A huge investment. Now, vendor A releases a security patch, or maybe they update their core API. Because your integration is totally custom, that single vendor change can suddenly force another 6 months of re-engineering work across your entire multi-vendor fleet,
Wow.
just to maintain basic compatibility.
So you're not just carrying software debt, you're carrying fragility. It sounds incredibly brittle. This lack of standardization, it's just a major barrier to scaling up.
Absolutely.
But hang on, isn't some degree of fragmentation maybe necessary? For vendors to innovate and differentiate their specialized hardware.
That's the critical tension, you're right. We absolutely need specialized hardware to perform specific physical tasks. But the argument is we don't necessarily need specialized intelligence baked into every single piece of hardware. The silos exist because the software, the robot's brain, is currently sort of inseparable from its physical body, the chassis. And that means very limited reusability. An object recognition system built painstakingly for Robot A cannot simply be copied and pasted onto Robot B, even if the task is similar.
This sounds like a problem that, open source should have tackled years ago, right? Why hasn't some dominant open source framework just unified the industry and broken these vendor chains?
Yeah, it's a good question. The challenge with open source in this specific space is often maintaining those really demanding enterprise requirements. Things like high-level safety validation, guaranteed performance levels, and importantly, robust support for hybrid cloud edge deployment, especially at scale.
Right, the stuff big companies absolutely need.
Exactly, and that's why there's this opening for a platform like GRID, which is promising that unification while crucially delivering those enterprise-grade tools.
Okay, so here's where we pivot. Let's talk about the proposed solution. Enter General Robotics and their platform, GRID. They call it a general-purpose intelligence layer for every robot. Now, that sounds like the elusive common language we've been waiting for.
It really is a profound shift, architecturally speaking. What they're aiming to do is decouple the intelligence from the specific hardware. So instead of that monolithic robot brain locked inside one machine, they present the intelligence as a composition of modular skills. Think perception, planning, control, reasoning, all accessible via standardized APIs.
Okay, let's get concrete on what a modular skill actually is. Is it just like a function call, a piece of code? or something
So
more sophisticated?
think of a skill as more like a specialized, reusable application, or maybe even a microservice. For instance, you don't build a whole new grasping mechanism logic for every single robot arm.
Right.
Instead, you build a highly tuned AI model trained purely on grasping dynamics. That model becomes a reusable skill.
I see.
You can then call that grasping skill, or maybe a perception skill designed to find red boxes, whether the underlying hardware is a big-wheeled manipulator, a flying drone, or just a static articulated assembly arm.
Okay, that reusability, that feels like the aha detail. If I perfect, say, a localization skill for one warehouse environment,
Yeah.
I could potentially just deploy it instantly to a completely different type of robot in a factory maybe halfway across the country.
Precisely. GRID is designed to provide that abstraction layer. It handles the unified deployment pipelines, develop in a sandbox, simulate it thoroughly, then deploy.
Okay.
And crucially, it supports hybrid deployment cloud, edge, or even fully on-prem, which is vital for managing latency and connectivity, especially when you're moving these data-intensive perception skills around.
And their claimed efficiency metric is, well, it's stunning, going from prototype to deployment in as little as 15 mines.
Yeah.
I mean, that tells me they must have drastically reduced the friction in that whole robotics DevOps pipeline.
Yeah, that 15-minute claim is certainly ambitious, especially for a completely novel skill from scratch.
Sure.
But it really highlights the potential when the platform itself handles all that underlying complexity, the integration, the simulation linking, the hardware abstraction. But, that speed only matters if the software running on these physical machines is fundamentally safe.
That's the perfect transition because these systems, they operate in the real physical world. Speed cannot come at the cost of safety. So how does General Robotics integrate validation and safety into this, rapid deployment architecture?
Right. Safety is baked in through a continuous feedback loop that's really centered on high-fidelity simulation. They rely heavily on simulation environments, citing tools like NVIDIA Isaac Sim, for instance,
Okay.
and also the generation of massive amounts of synthetic data. This allows you to rapidly test and adjust perception and control models right there in the simulation.
Without risking hardware.
Exactly, without risking expensive hardware or interrupting real-world operations. It's critical.
Simulation definitely helps prevent failures. But look, in large-scale enterprise fleets, failures will inevitably happen sometimes. What happens when a multi-robot system makes a mistake? Enterprise users, they need clear accountability, right?
Yeah, absolutely. Non-negotiable. And the platform reportedly makes safety a first-class concern by building in things like blame assignment and interpretability directly into the architecture itself.
Interesting.
So when something goes wrong in a traditional siloed system, you often just get some generic error code, right? Good luck figuring that out.
Yeah, cryptic at best. So what does blame assignment actually look like practically for, say, a manager reviewing an incident report?
It means the system provides a kind of forensic trace. The logs don't just say, robot failed to pick object.
Okay.
They actually trace the execution path back to the exact skill, maybe the specific version of the vision model or the planning algorithm, that delivered the faulty output or made the wrong decision.
Ah, so you can pinpoint the cause.
Precisely. This immediate traceability allows for really targeted updates, rapid implementation of recovery logic, and crucially, maintaining that accountability in these complex multi-agent scenarios. This is totally non-negotiable when they're aiming to scale up to support large enterprise fleets, which
Right.
they claim they can handle. Up to 25K plus concurrent requests for inference. That's serious scale.
That kind of scale requires trust, definitely, and interpretability helps build that trust. Okay, now let's move up a level to the interface. The next evolution isn't just about making the robots work together smoothly, it's making them accessible and understandable to us, to humans. And that brings us to large language models, LLMs, and natural language interfaces.
Yeah, this is where robotics really starts meeting conversational AI. And what's fascinating here is that the LLM isn't intended to directly control the low-level physics. It's not running the motor driver second by second.
Okay.
Instead, it acts more like the high-level manager or planner. Its job is to translate that often amorphous human intent into precise, actionable sequences for the underlying skills.
So the human operator potentially shifts from needing to, hand code Python scripts to just talking to the system. Give us that scenario.
Okay, let's imagine a complex warehouse task. Instead of, programming specific movement waypoints and object detection parameters line by line.
Hmm.
The operator might simply say something like, go to shelf C, pick the red box, and bring it to zone 5 for inspection.
Right, that's maybe 3 or 4 complex steps packed into one natural sentence. How does the LLM actually turn that sentence into physical action?
Good question. So the LLM first handles the intent parsing and task decomposition. It recognizes the sentence involves a sequence. Navigation first, then localization, then vision detection, grasping, and finally another navigation step.
Okay.
It then translates these abstract steps into specific API calls to those modular skills we discussed earlier. It orchestrates the flow. Okay, call navigation skill version 1.0. Once that succeeds, call vision skill 2.1 to localize the red box. Once it's localized, call grasping skill 3.5. It manages that sequence.
This immediately raises a really crucial point, something the sources call the symbol grounding challenge. The human word red box is just an abstract symbol. How does the system ensure that symbol maps accurately and, importantly, safely to a specific physical object in the real world?
Yeah, this is arguably the hardest part. It requires incredibly tight integration between the language model's output and the robot's perception systems. The plan generated by the LLM is really just a cognitive framework.
Right.
Before any execution happens, the system must validate its physical feasibility. Is the thing identified as the red box actually within the robot's reach? Is it too heavy for the gripper? Are there obstacles?
Collision constraints. Yeah.
Exactly. The system has to map that symbolic word, red box, to the actual pixel coordinates found by the perception skill in the camera stream, and then localize that object in 3D physical space.
And if the vision skill, say, fails to find any red box, or maybe it finds multiple red boxes, the command just breaks down.
Well, it would in a brittle system, but for robustness, this is where that conversational loop becomes essential. The robot, or more accurately, the LLM acting on its behalf, needs the ability to ask clarifying questions.
Like what?
Like, okay, I see a small red box and a large red box on shelf C. Which one should I select? Or perhaps if it encounters an unexpected obstacle, it needs recovery logic built in. Uh-oh, the path to Zone 5 is currently blocked by a forklift. Should I wait or perhaps reroute to Zone 6?
Got it.
The LLM enables this much more dynamic, adaptive kind of conversation.
So this is really more than just command and control. It's starting to look like collaborative problem solving between human and machine. Now, if we connect this level of modularity in natural language processing to the really big picture, we are talking about multi-agentic AI orchestration.
This is the ultimate payoff, I think, for the listener to grasp. Multi-agentic orchestration fundamentally means humans, intelligent software agents, and physical robots all collaborating pretty seamlessly, operating under a shared, unified cognitive framework. And that framework is defined by the orchestrator.
Okay, so the orchestrator is like the conductor of this very complicated opera. What exactly is its job?
Well, the orchestrator, often powered by agentic AI, dynamically assigns the overall mission. It might delegate complex reasoning tasks, like calculating the absolute optimal route or scheduling multiple jobs to purely software agents. Then it delegates the physical execution, the moving and manipulation to the robots, and critically, it leaves the ultimate oversight and final decision-making authority with the humans in the loop.
And GRID's role here is pivotal then, because it provides that common abstraction layer we talked about.
Right.
It effectively turns the physical capabilities of any compatible robot into these modular AI skills, accessible via standard APIs.
That's the absolute key unification point. Because the robot itself is abstracted into these callable services, the orchestrator doesn't really need to care about the specific hardware vendor underneath. It can command a physical robot using essentially the same high-level commands it would use to command a piece of intelligent software performing, say, a logistics calculation. The physical machine starts to become genuinely interchangeable from the orchestrator's perspective.
So, okay, this is fundamentally how we could replace the current ecosystem of, very specialized, siloed robotic tools with something closer to true general-purpose robotic platforms. It streamlines the entire life cycle. Building, deploying, managing, and commanding them.
That's essentially the thesis presented in the sources. The aim is to solve the silo problem, remove that painful vendor lock-in, and make robotics a much more scalable, composable technology, rather than just this endless series of custom, one-off engineering projects.
But let's just apply a critical lens for a second before we wrap up. When you unify everything onto a single platform, even one that offers this kind of advanced blame assignment we discussed, aren't you potentially introducing a new kind of risk? Like a single point of failure or maybe a centralization of control?
That's a really crucial architectural consideration for any large enterprise adopting this. You're right. If the entire intelligence layer, the GRID platform itself, were to somehow fail, you absolutely risk paralyzing the entire fleet, regardless of the physical health of the individual robots.
Right.
The source material does hint that supporting that hybrid deployment model cloud, edge, on-prem, is their primary hedge against this very risk. It allows essential mission-critical skills to potentially run locally on the edge or even on the robot itself, even if connectivity to the central cloud is lost.
So it's a balancing act.
It's an ongoing balancing act, yeah, between centralization for efficiency and unified control and distribution for robustness and resilience.
Fascinating. Okay, so wrapping up. You have this common intelligence layer, you have validated plug-and-play skills, and you potentially have a natural language interface managing the whole show, dynamically assigning tasks across different agents, both software and hardware. It seems like it could completely change the economics of fleet deployment and, maybe more importantly, how quickly businesses can adopt advanced automation.
And this leads to, I think, an important question for you, the listener, to consider, especially as these platforms continue to mature. If a general-purpose orchestrator can command a physical robot to perform a task using the very same language, the same modular skill API, it uses to command a sophisticated software agent to optimize a schedule. Well,
Okay.
when does the practical and operational distinction between a physical robot and just a piece of intelligent software truly start to blur?
Yep.
That's really the frontier we seem to be moving toward. And it's definitely something to mull over as you watch automation continue to advance in the coming years.